Anyway, yeah, so as Alex said, I'm Daniel Bowring. I work at Fermilab. Uh, Perhaps you are used to thinking of Fermilab as a particle physics laboratory where we use large accelerators. We also have a significant quantum program that I'm a part of. So what I'm going to be doing mainly is talking about what we are doing at Fermilab in collaboration with a lot of other institutions, including yours, in the area of quantum. So like, what is it? What's the intersection between high energy physics, particle physics, and quantum information? Okay, so we'll find out together. Okay, so it's a big group, getting bigger all the time. We, in particular, in this specific talk, I'm referencing work that is done at Northwestern, at SLAC, at Purdue, at Madison, and then here's the Fermilab group. This is an old picture, of course. This is not everybody, but I like it because there's my baby. Okay. So when we talk about particle physics, maybe you think about CMS or one of these giant collider detector experiments, right, at the LHC, where the term high energy really obviously applies, right, where you've got these very energetic collisions. So these are 13 TeV proton collisions at the Large Hadron Collider, and in such a situation, these things are very violent. And classical detectors in that sense are usually pretty good, right? We're not trying to detect faint signals there, but there are other things that large scale physics projects do that are not quite so violent, right? So one of the things that we want to do at Fermilab is create the world's most intense beam of neutrinos, send those neutrinos all the way through the Earth to a lab in South Dakota. So Illinois to South Dakota, that's a distance of 1,300 kilometers. So that we can measure properties of neutrinos like oscillation very precisely, right? So here what we're doing is using our proton beam to collide with a fixed target, create a beam of neutrinos and characterize them here in our basement, and then over here at the bottom of a mine shaft in South Dakota, and compare the differences. So why do I consider this to be a rare process or a faint signal? Well, you know, the mean free path of a solar neutrino in lead is like more than a light year, right? So neutrinos don't interact very much. So our ability to capture rare interactions or faint signals is important. And the context in which we are giving this talk is a focus on dark matter. All right, so I'll talk about what dark matter is, but there's a lot of work recently done on the applicability of quantum information and quantum sensing to the problem of dark matter. There's a couple of review articles here that I will not get into, but it's a great place to start. And if you all are going to post this talk later, I've got a bunch of links here. These are all, you know, clickable hyperlinks. Okay. So my thesis statement, right, is that quantum information technology is necessary to meet current and next generation challenges in particle physics. And so I'm going to talk about dark matter because that's my thing. There's a lot of other work going on at Fermilab, right? So for example, we have people working on cold atom interferometry for sensing tasks. So right, entangling the wave function of strontium atoms over very large distances and times for very sensitive sensing, if you want. We have people working on building new kinds of qubits with very long coherence times. We have a lot of different kinds of quantum projects. There's a big, strong theory department. People want to use quantum computing for data analysis and high energy physics experiments. There's a lot, and I don't have time to talk about any of that except for sensing for dark matter. So that's the focus of this talk. So I have to review dark matter because when I asked who has a background in dark matter, nobody raised their hand in this room. Fine, no problem. Then we'll talk about superconducting qubits because when I asked about qubits, only a few people raised their hand in this room. Again, fine, no problem. But so there's going to be a lot of pedagogy in this talk, yeah? And that's just because it's the price we pay for doing multidisciplinary work. Fine. So then we're going to put it all together, and I'm going to talk about what we are currently doing with quantum information in the space of dark matter detection. And so that means a lot of like thinking about detectors, characterizing detectors, trying to design new kinds of detectors. And so we're kind of taking the standard quantum information toolkit and turning it on its side and looking at it with a new perspective, because we have different goals than just trying to build some colossal quantum computer, right? So we're friends with the quantum computing people. We talk with them. There's ways that we that we do work for each other or exchange information, which is productive. But my goal is not to build a big, cool quantum computer. My goal is to find dark matter. And so the ways that I use these tools are going to be different. And then I'm going to give you a rundown of all the cool work that's happening in our program, or at least a lot of it, and then questions. Okay. So a goal of this talk is communication between subfields, and it is hard. We've been trying to do this for years, and it never gets any easier, right? So over here I've got a dog which has a lot of cool tools, right? This dog has a lot of cool tools, and the dog wants to really use those tools to do interesting work. And this dog over here has a cool problem that she wants to solve, and is thinking, man, if only I had the right tool to solve this puzzle. So if you get these dogs together in the same room, then they publish a lot of papers, or I don't know, my metaphor breaks down, but you get the idea. Okay, so let's talk about dark matter. I'll give you just a couple slides on dark matter. I'm not trying to convince you that it exists. I'm sort of treating that as axiomatic, but at the very least, if you've never seen dark matter before, let's talk about it for 1 minute. There's other maybe more empirically motivating examples I could give, but this one's cool and sort of visceral, right? So this is a picture of two galactic clusters that are in the process of colliding. You got one over here, you got one over here, and they're going bam, bam. This is an optical image taken through the Magellan telescope of these two clusters, and so you can see all these things are galaxies now. So this is the big process that's happening. And then over here, if you change the filter on your telescope and you look at, instead of the visible optical spectrum, you look at X-rays, you can see all the plasma involved in this galactic collision process. So you can see you really would not want to be there. It's a very violent place right now. But you can see where the plasma is concentrated in this collision. Okay, so you get the idea, looking at the X-ray spectrum, that the mass in this system is concentrated here and here, where the hotspots are, right? Because that's where all the matter is. Like the plasma that is the consequence of this collision process is the most dense thing in that vicinity. And so if here's where the plasma is and here's where the plasma is, you would expect naively for there to be where the mass is and there to be where the mass is. However, if you do gravitational lensing analysis on these images, you get the contour lines in green that are shown here. And okay, so here, what do I mean by gravitational lensing? Well, mass bends light, and the extent to which mass bends light, you can use general relativity to look at optical images and to look at other images and figure out how much light is bending in a particular region of space. And so if you do that kind of analysis here, you see the green contours, right? And you see that most of the mass should be here and here. It doesn't line up, right? So if you look at the lensing contours on the right-hand side, and you look at the X-ray plasma map on the left-hand, on the right-hand side, contours on the right, X-ray on the right. If you look at those two, you see that they don't match up. You see that there's some invisible mass in this system that is responsible for bending all this light. It's not where we can see it. Hey, that means it's dark. Okay, so that's what we mean when we talk about dark matter. There's lots of other evidence, like I say, but we have really good reason to believe that there's a bunch of matter out there that we can't account for, that is invisible to us. Some people like to call that clear matter instead of dark matter, because of course you can scatter light off of a dark thing. But anyway, the point is there's stuff out there that we don't know how to look for it. And it's a lot of stuff, right? So if you do a matter energy budget for the whole universe, you can see that about 70% of it is dark energy and 25% of it is dark matter. I'm rounding here. And then a little bit under 5% is regular matter, that is to say atoms. That's not a lot, right? So dark matter is out there. We have a lot of indirect evidence that it's out there. And when we think about it, we think that there must be quite a lot of it in relation to normal matter. So it's weird that we don't know what it is or how to look for it. We know some things. We can infer from a lot of different measurements that it's cold, that is to say it's not relativistic. It's non-baryonic, that's not made of protons or neutrons or whatever. It's made of particles, right? So a lot of people like to say, oh, maybe you just don't know general relativity. But every test of general relativity that we can come up with, we pass with flying colors, right? That theory is solid. It's probably not modified gravity. It's dark. It does not couple to electricity and magnetism, right? So the electromagnetic force doesn't know how to talk to dark matter. And it has mass, right? Hard to do this without explaining, hard to explain all of what we see without mass, because of course it's a gravitational interaction that we observe most when we talk about dark matter. Okay. That's not a lot of, like, this list doesn't really narrow it down, right? It's a place to start, but it doesn't give us a lot of clues. So what are some theories? Well, there's a lot of theories, right? And so this is a paper published in 2017 that tries to summarize the state of dark matter. And in the intervening 6 years, there's only been more proposals. And so I would imagine that this map is now even more complicated. But every blue line you see here gives some idea, describes some theory, right? Some idea that people have of what dark matter might be. You can see there's a lot of blue lines, so there's a lot of theories. I'm not going to explain every one of them. The other point I want you to take away from this is, look at this energy scale. Over here, you've got 30 solar masses, right? So that's people thinking about black holes as a potential explanation of dark matter. And then over here, you've got zepto-electron volts, which is, what is it, 10 to the minus 15 EV? So it's a very broad range. And what I've been trying to impress upon my colleagues at Purdue is, if you have some technique which allows me to probe even a tiny little slice of this mass range, I will take it, because I'm desperate, because this is a lot of territory. And there's no one experiment that you could concoct that would be sensitive across all of these orders of magnitude. Okay, so how are we addressing this huge parameter space? Well, one way is to look at scattering, right? So if dark matter is heavy, if it is a WIMP, a weakly interacting massive particle, then maybe you can bounce it off of a heavy nucleus and look for some recoil signature, some electrons or photons that are given off in this process. And in fact, Purdue has a hand in the xenon 1-ton experiment, which is doing just that. Okay, so xenon 1 ton, you get 1 ton of liquid xenon, you put it in a jar, and then you wait, right? You make it very cold, and you wait for these very, very rare scattering processes that you can detect using the photomultipliers you see here and other things, okay? All right, so that's one way to do it. That attacks sort of this, the top red band of this, it's sort of a semi-quantitative map of the parameter space that I'm talking about, right? So on the horizontal axis here, you've got mass in mega electron volts, big MeV, right? Where you've got 1 in the middle and 10 to the 3 over here, that's a GeV, and then 10 to the minus 3. And then on the vertical axis, you've got recoil energy. So the more of a violent collision you can expect from your theory, the higher the recoil energy will be. If dark matter interacts weakly, if it's less massive, then you get more gentle recoils until you don't get recoils at all. You get something else. Okay, so this is a big map, and I'm just trying to explain to you some of the techniques. So scattering, that's that top pink band up here. Yeah. Okay. If you need to look at lower recoil energies because you think dark matter is less massive, or the interaction potential between dark matter and regular matter is lower, then maybe you think about ionization in semiconductors, right? And so that's the subject of the cryogenic dark matter. So here, what do we have? We have a dark matter particle that comes in, it bonks into an atom, and now instead of some violent process like in the middle of a particle detector, we're talking about something more gentle. We're talking about creating phonons, right? So we're talking about lattice vibrations that liberate electron hole pairs, and then we can detect those in some semiconductor measurement process. Okay, so that gets us a little bit lower on this plot. This is hard, by the way. And then to get into this region right here that I've circled in red.
What's the size of that germanium?
Oh, an individual detector. Where's Ryan? Ryan works on this directly. He's left. All my Fermilab colleagues have gone off. Yeah, so we're talking about several cubic centimeters. And then you can assemble large collections of them if you need to get to larger scales, right? And that's the point of the cryogenic dark matter experiment. Okay. So at low energies and at low dark matter target masses, we need new strategies with an emphasis on low detection thresholds. So we're talking about trying to detect signals below an EV, or below an EV, and low noise, right? So it's not enough to be sensitive to signals below an EV. We need to be sensitive to them even when it's a real large physical system that's going to have, I don't know, depends on the setup, shot noise or vibrational noise or whatever it is. And so this is the region, this region I've circled here, that's the one where we want to think hard about quantum information science. Okay, so I'm telling you all this because I'm trying to motivate this idea that we are really open to adopting new technologies, because again, the parameter space is huge and our experimental requirements are increasingly difficult to meet. Mike, do you have a question?
Yeah, so I hear what you're saying, but it still depends on what the mechanism in cross-section is.
Yeah.
So is the cotangents is the assumption that they interact with weak interactions, or
There's so many theories. Remember, I showed you that plot where there were so many theories, right? And so, yeah, so you could talk about standard model interactions. There are some modifications to the standard model that some of these processes give you. But because there's so many theories, it's very hard to talk about the specifics, right? So if we were looking for
if I were designing a detector,
yeah,
I'd design it around whatever process that I'm looking at, there's no sensitive.
Right. So broadly speaking, there's two different kinds of processes, right? One is a dark matter particle which can bump into something, and that's sort of on the massive side, right? Heavier than an MEV, and there we're looking for recoil, and then as you
Bump means an interaction.
right. Yeah, no, I understand, right?
So what is that?
So the reason I'm being vague is that there's different theories that assume different interactions, right? So it could be a strong process, it could be a weak process. If you get down to low masses, like below an EV, let's talk about below a milli-EV, then there's electromagnetic couplings that we want to study as well. So very model dependent. There's modifications to Maxwell's equations that you can talk about. So way down on the mass scale, like way down even past this plot, you've got wave-like dark matter where it's a coherent signal and you're trying to detect things, just small numbers of photons that shouldn't be where they are, or something like that, anomalous. So anyway, so there's a big buffet, I guess, let's say. So the search for low mass dark matter benefits from sensitivity to signal quanta, and that quanta, as Mike was alluding to, could be a bunch of different things. It could be photons, it could be phonons, could be magnons, could be something else, right? We are at this stage looking for tools, like I said. And if you tell me about a tool and you tell me in sufficient detail, then I can match that to a theory and we can test the theory. Okay, so I want to talk about the work we are currently doing at Fermilab, and that means a focus on superconducting quantum bits. And so I will give you a very quick overview of superconducting qubits, because I think not everybody works with them. And then I will explain why we think they're relevant for dark matter. So this is going to be really quick. Can't have a physics talk without a harmonic oscillator. The irony of me saying let's start, and it's like 20 minutes of my talk, it's not lost on me. But anyway, here we go. Here's an LC circuit. That's a harmonic oscillator. In a harmonic oscillator, you've got energy levels that are very well spaced. Each energy level is 8 omega apart from each other energy level. What does this mean? It means that if I take a photon of frequency omega and I dump that amount of energy into this oscillator, then I will excite any transition between any two levels that are adjacent, right? So I can't control which level I'm exciting when I put in light of a particular frequency, if that frequency is the resonant frequency of the oscillator. Okay, so that's fine. That's a good place to start. But now I'm going to replace the inductor in my circuit with a Josephson junction. And if I do that, you can do some math here, starting with the Josephson equations. This is just algebra, right? Moving terms around. What you end up with is an assessment that the inductance that comes from this Josephson junction is nonlinear, right? Because you've got this cosine phi term in the bottom that doesn't behave nicely. So why is it interesting to have a nonlinear inductance? It's because now, all right, here I'm comparing a quantum harmonic oscillator with an anharmonic oscillator that I get from using that nonlinear inductance. And you can see now that the energy levels are spaced differently, and each two energy levels have different separation. And what this means is that now my level transitions are addressable. That means that I can excite a transition between the ground state and the first excited state with one frequency. Or with another frequency, I can excite a transition between the first excited state and the second excited state. But I'm not going to get confused, right? Each one of these transitions is something that I know, and I have control over the frequencies that I'm sending into the system. And so I can excite transitions from one level to another, no problem. All right, so now if we have addressable energy levels, now we can engineer a two-level system where I only have the ground state and the first excited state, and I'm not really worried about those higher order states. 0 and 1, that looks like a bit, right? I'm being a little bit glib because there's a lot of material to cover. There's of course more details, but this is, all right. So then if we write out the Hamiltonian, maybe we can understand the dynamics a little bit. You've got sort of kinetic looking terms that have to do with the charging energy of the capacitor and the Josephson junction. And then you've got a cosine potential, right? So again, comparing the quadratic, the parabolic potential of the harmonic oscillator to the cosine potential of the anharmonic oscillator. And that gets you some different energy levels. One of the things I want to point out is this idea that the charge that rattles around at that capacitor is important. Okay, so here's the Hamiltonian. Now I've got it in terms of the number of Cooper pairs that are moving back and forth in the system. Again, I'm skipping some steps. You're just going to have to bear with me. And then I've got this term, which is basically about environmental charge in the system. And that's charge that maybe I don't control so well that bumps around in the vicinity of that capacitor. And then I've got the potential term here. Okay, so why is that important? Well, the energy levels in the system, naively, unless you are very careful about picking these energy terms, the energy levels in the system are going to depend on the environmental charge in your system. You can engineer that away. So you can say at different ratios of the charging energy or the Josephson energy to the charging energy, you can get less and less and less dependence on the environmental charge as you make this ratio higher and higher and higher. Okay, so at low energy ratios, you get qubits with more charge sensitivity. At higher energy ratios, you get qubits with less charge sensitivity. And that charge sensitivity is going to come up later. So remember about gate charge and charge sensitivity, because we're going to talk about it. Okay, so that's preamble. Any questions? Everybody's cool? All right. Okay, let's keep going. Next topic. How do we use qubits to detect particles? So I'm going to give you a very short summary of 3 recent papers, and then we'll talk about the work we're doing at Fermilab. Okay, paper number 1. This is out of the MIT Lincoln Lab group led by Will Oliver, in which they demonstrate that the energy relaxation rate of qubits, the decoherence rate, I guess, if you want, of qubits, is influenced by the ambient ionizing radiation that is incident on a qubit. So what do? They take a 64 copper source with a half-life of 12 hours, and they put it right next to a couple of superconducting qubits. And they just measure T1, or the energy relaxation rate. They measure that over a period, repeatedly, they measure it over a period of hundreds of hours. And what they see is as the source decays, the energy relaxation rate decays too. So that is to say, the qubit becomes more coherent the less radiation is present in the system. Does that make sense? Did I say that backwards and upside down? That the presence of the more ionizing radiation you have in the system, the less coherent you can keep the qubit. It's a problem. And they have a really nice model for why they think this works, right? It has to do with the generation of quasi-particles in the system, right? So the relaxation rate that comes from quasi-particles, broken Cooper pairs in the Josephson junction in the qubit, right? So electrons that move back and forth, that tunnel back and forth in the Josephson junction. You can imagine that they do this in an uncontrolled way, and so you don't want that. That sort of creates problems for the information stored on your qubit, something to avoid. So they relate that relaxation to the density of quasi-particles in your qubit. And it's a pretty direct relation, and they've got a nice analysis that comes out of that. But the thing, I'll read the paper if you want details, but I'll just call out this sentence. Albeit a small effect for today's qubits, reducing or mitigating the impact of ionizing radiation will be critical for realizing fault-tolerant superconducting quantum computers. Okay, so we have this idea that ionizing radiation is a problem. Paper number 2, ionizing radiation causes correlated errors in qubit arrays. And so this is a paper out of Robert McDermott's group at University of Madison, University of Wisconsin in Madison. They have a mildly charge sensitive qubit there's that energy ratio that I was talking about before. And what do? They make some randomly measurements on the qubit to map that gate charge, that Ng, right, that quantity that I was talking about earlier. They map that onto the qubit parity. So what they can do is they can measure to within some aliasing the amount of gate charge that fluctuates in the qubit over time. Then what do? They bring a radioactive source nearby, and they see that there are space and time correlated jumps in multiple qubits. So here's a schematic of a 4-qubit chip, and you can see that some of them are near neighbors and some of them are far neighbors. The horizontal axis on this plot is hours, and the vertical axis is offset charge, or that environmental charge I was talking about. And you can see that over time, there's big jumps, little jumps and big jumps in the amount of charge that's sort of like rattling around in the qubit. And sometimes you get jumps that are correlated in time. So these two insets are blown up here, and you can see that right here, you've got 2 qubits that register the same charge jump at the same time, and then another one on the back end. And then you can see it happening again here on this other inset. Okay, so what's happening here? We think that each time an ionizing particle interacts with the qubit chip, it's depositing on the order of 100 keV of energy in the substrate of the chip. And you generate 1 electron hole pair per 3.6 EV. So that's a lot of electron hole pairs. That's a lot of quasi-particles, if you want, that are generated during these interactions. And so you get these bursts in time, sort of like these step functions in the density of non-equilibrium quasi-particles in your chip. And that's causing decoherence. And moreover, it's causing it in multiple qubits at once. Why is this important? If you want to build a fault-tolerant quantum computer, you can't have that, basically. That the error-correcting codes for quantum computing, Mike, is that a hand?
Yeah, it is.
Okay, go ahead.
So it's great that they could write a Nature paper about it.
Uh-huh.
This is just, running 20 years of transmon development in reverse, right? You're going towards a charge qubit limit away from transmon sensitivity.
Yeah.
And basically putting back in non-equilibrium distribution or increasing the non-equilibrium distribution of
yeah.
So
I think that there's actually an important distinction that this paper and its predecessor makes.
Okay.
That's a little bit that complicates your your assessment, and that is that so we know about tunneling back and forth of quasi-particles in a Josephson junction. That's a high rate process with low charge. And the nice thing about these measurements is that they can quantify the amount of charge that happens in these tunneling processes during a burst event. And so there's actually 2 flavors of charge tunneling that happens. There's the low-level stuff that we've always known about and that we built transmons to prevent. And that's just like normal, traffic. And then there's the large stuff. So the idea that ionizing radiation creates these bursts and that they have a material measurable effect on the qubits, it's a bit of a different thing. It's much higher charge amounts at lower rates. So the quantitative difference is we're talking about
it's quantitative. I don't think it's qualitative.
Yeah, quantitative.
Yeah, it's not qualitative.
Okay, I agree.
It's not a bad thing. I'm just saying
Yeah.
this is taking a transmon, making it less of a transmon.
Yeah.
So you can send something. That wasn't really my question.
Uh-huh.
The question that's
Okay.
These are known interactions, meaning that was generated, if you put the source there, was generating
Mm-hmm.
the interaction in qubit material.
Yeah.
And so it goes back to my earlier question. This is cool if you know what you're looking for.
Right.
And how do you translate it in when you don't know what that interaction is?
Yeah. The analogous process in high energy physics is the development of semiconductors for dark matter detection, right? Where the reason we started thinking about semiconductors is because they have a nice low band gap. And so we start at that point, and then we do several decades of detector development and theory work to figure out what a nice low band gap, low threshold measurement gives you, which sections of parameter space it carves out. But as I said, when I showed you the picture of the dog with the tools, right, we're really at the point now where we're trying to assess what our tools are. And I will get to some of the more the subtleties of your question later in this talk when I tie this all together with the group work our group is doing. Okay. One more. This is a nice one because, so this is a paper out of Google, and they use the word catastrophic in the title, which lets you know that it's going to be fun and interesting. So ionizing events in this paper wreck information stored on qubit processors. So here they've got half of a Sycamore processor, that's 24 qubits. Anyway, there's 24 qubits in this. I think a Sycamore processor is 54, so you do the math, but some of them are not present. Anyway, the point is, 26 qubit subset of a Sycamore processor, fine. Prepare all the qubits in the first excited state, in the one state, wait 100 microseconds, and then simultaneously measure all the qubits, and you'll see that some of them erroneously are in the 0 state. So they can do this very fast, and they repeat it for a long time, and they can map, in this plot here, the number of simultaneous qubit errors on the vertical axis versus time in milliseconds on the horizontal axis. And so what they're seeing here is that, you know, here their qubits are minding their own business in their dilution refrigerator, nice and cold. All of a sudden, something happens, and you go from a map of qubit errors, which is basically no qubit errors, to one in which there's a hotspot right here. Boom. And then that hotspot propagates out. And when I say hot, I don't mean temperature, I mean error percentage, right? That propagates out to the chip until these whatever they are, those perturbations thermalized away, and then you sort of get back to your normal operating state on a time scale that is measured in milliseconds. All right. So to quantify this a little bit, the event rate that they see when they do these measurements is about 0.1 hertz. So once every 10 seconds, you get something in their lab, their perfectly normal lab that doesn't have radioactive sources in it. About every 10 seconds, you get something which completely wipes out all the information on their processors. So they say in the paper, right, that this is long compared with T1 with the coherence time of the qubit. So maybe you don't worry too much if the qubits don't ever have to talk to each other. But if you are trying to do error-corrected quantum computing, fault-tolerant quantum computing, this is short with the hour-long timescales that those algorithms require. And so this kind of correlated error is a problem for operating quantum computers in general. And everybody who's talking about this has more or less the same model, which, well, I'll get there. But anyway, you can see in this cartoon here, right? You've got some particle, that's the red arrow, that passes through the substrate in your qubit. It liberates a bunch of phonons, and then those phonons create excess quasi-particles that travel through your Josephson junction and mess with your information that's stored in your qubit. Okay. All right, so these are examples of qubits being used as particle detectors, right? It's a trivial application. You could also have a Geiger counter or a photon, you know, a photodiode or whatever it is. Like, there's easier ways of finding X-rays in the world, but that's not the point. The point is that we know that qubits are capable of detecting particles. Now we just want to detect interesting particles, right? So what are the next steps? For one thing, if we're going to, yeah,
So
go
at
ahead.
this point,
Yeah.
these qubits used as a detector of ionizing radiation, they are not more sensitive than the existing detectors.
In the Google paper, it's just transmons,
Right.
right? They're just using like the qubits you use for quantum computing, they're using in this analysis. Yeah.
I'm saying in terms of the demonstrated detection, I mean, of course, Heinfeld have very mature sensitive detection.
Okay, so in terms of the energy threshold for these detections, no, it's not competitive with the stuff I was showing you earlier for the cryogenic dark matter search or Xenon 110 or anything like that. We're trying to figure out what the energy threshold is, and I will tell you some more about that a little bit later. So, was there another question? Yeah, Leonard.
Also, these high energy events,
Yeah.
either they are frequent enough to affect T1 in a sort of in a measurable way, or they create this catastrophic event which propagates through many qubits. So you sort of have, again, averaging over the other sort of over the number of qubits. Now, you interested in very low energy events.
Yeah.
So how that sort of moves on.
Yeah. So again, I think it's a technical question that we need to address with a full-on program to characterize these detectors. But so yeah, in one experiment, we're looking for wave-like dark matter, and the event rate is like 1 an hour, right? milli-eV energies. The number of events that you would expect from theory in the xenon 1-ton experiment is not more than a few a year, right? So yeah, the uptime required for these experiments is long. Maybe not impossible, but it's a different mode of operating than I think people are used to when they think about superconducting qubits. So that's another thing that we have to assess.
For example, effect of T1 you cannot do if you have one event and longer than T1, much longer than T1. Right? So
Yeah, no, that's right. If T1 was the only parameter that we were looking at, then we would be in trouble. But I think it's not, right? So parity errors are another thing. Anyway, so I hope that I will satisfy you a little bit more with some of the other slides here. Again, I was making the analogy to Mike that that when we decided to develop, the physics community decided to develop semiconductors for dark matter searches, it was a multi-decade effort to characterize these things, to really understand the microphysics of what's going on inside the material before we could deploy them with confidence in a detector scheme where we could say, we ran this for a year. Here are the backgrounds that we've characterized extremely well. Here's the sources of noise in the system. Here's the response. We've modeled it with software. We've done all these things. And now we're just starting on that journey again with a new technology. So it's a long road ahead of us. So for one thing, we need to think about detector backgrounds. What do we mean when we talk about ionizing radiation? What is it that's causing those decoherence events in the papers I showed you? Well, it's probably one of two things: gammas and or cosmic rays. So for gammas, everything's mildly radioactive. You've got thorium-232 or potassium-40 in the concrete in your building, and everything's sort of mildly radioactive, except for the stuff which is manifestly not. It's in the air, it's in your fridge. And when one of those gammas finds your qubit, it's going to deposit energies which vary depending on the isotope, blah, 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 but on the order of 1 MeV, mega MeV into your chip. And the event rate, very similarly, roughly, is about 1 per centimeter squared per second, okay, for a typical terrestrial environment. Obviously, if you take a big chunk of plutonium and put it in your lab, it'll be different. Cosmic ray muons are the other main source of ionizing radiation. In that sense, what's happening? Violent processes happening outside of our galaxy send particles into space. Some of those particles interact with the Earth's upper atmosphere and create particle showers through the strong interaction. And some of those particles end up reaching us on Earth as muons. These muons are, let's call them on the order of 100 keV. And the flux at sea level, at the surface of the Earth when you're outside, is about 1 muon per centimeter squared per minute. Okay, so rarer, lower energy, but these also cause, so these are also causing coherence problems. So these two types of ionizing radiation are the ones that we are thinking about the most. And I want to point out that these muons also cause problems for classical computing. If you have a bit stored on your hard drive, like on your classical, regular old bit, maybe if all you want to do is look at pictures of dogs on the internet, like I was doing when I made these slides, it doesn't matter whether some of those bits just kind of flip sometimes, right? You've got error correction on your computer, you've got backups, blah, blah, blah. If you are, I don't know, in charge of a nuclear submarine, and the computer on that submarine has an important job to do, then maybe you don't want any bits to flip accidentally. And so they actually do, for very sensitive applications, you do need to correct against the source of error. Otherwise, again, we hope that the nuclear submarines are not sensitive to 1 bit flipping, but I want to be sure. Fine. Okay, so what's the decoherence mechanism that we're talking about? Well, it looks like this, right? So there's some particle that is outside of this chip, and all of a sudden, boom, it interacts with this chip. It scatters off of something in your substrate. That scattering event creates phonons that bounce all around in your substrate that are reflected. Those phonons liberate Cooper pairs in the superconductor. Those Cooper pairs tunnel through the Josephson junction, or the quasi-particles tunnel through the junction and cause problems with decoherence. So this is the working hypothesis that a lot of us are starting to gravitate towards for why these events happen. And as I said, some of these papers will explain the model to you for, in more detail for what's going on. Okay, so now what are we doing at Fermilab with that hypothesis? Well, we have underground labs. Why do we have underground labs? It has to do with the neutrino experiments that I was showing you earlier, right? So there, when I said that we create neutrino beams in our basement and we send them to South Dakota, this is what I mean. you need to have beam interactions below the surface of the Earth that will point the neutrino beams in the right direction to reach our far detectors. And that means that we have already excavated caverns underneath Fermilab. We didn't need to build these for quantum information, but they're useful there, right? So here's a 3D view. You can see a 300-foot mine shaft. It's mine shaft. It's an elevator shaft, 107 meters. So we're working underground. And in that environment, we have a clean room and a dilution fridge, So this is a 10 millikelvin cryo concept dilution refrigerator. There are some aspects of it that are not standard. For example, there's this giant block of lead right here. But otherwise, there are some familiar features. We have a class 10,000 clean room. We've got a low background rate that's been extensively characterized. Underground, what do we get? Why do we? It's annoying enough to keep a dilution refrigerator running above ground, even in a lab basement. Why do we go 100 meters underground? Why do we put on the hard hat? Why do we, assume all these extra safety risks and whatever? It's because it gets rid of our muons, right? So the muon rate is attenuated by a factor of about 500 underground at this facility. And that means now that we can decouple the effect of X-rays from the effect of the muons on these devices. And that means that we can get at a much more precise estimation of our backgrounds. The other thing I want to point out is this lead shield, this big old casket on rollers. So there's like a kind of a railroad track underneath this thing. And we can pull this thing so that it totally encloses, gives a nice warm hug to our dilution refrigerator so that there's 4 pi coverage of lead blocks all around the fridge. And that combined with this lead shield that's inside the fridge means that our payloads down in this area are very well insulated from gammas. And the effect of putting this thing underground means that we're well insulated from muons. And then, of course, we've got detectors for catching the muons that, it's for understanding the muon flux down there and for understanding the gamma flux. So, as I said, well-characterized backgrounds and also really nice shielding. And so because of this, we are sort of well-positioned. This, by the way, existed before our quantum information program too, because we were trying to characterize dark matter detectors, semiconductor dark matter detectors using this facility as well. So what we did when we decided to get excited about qubits was to put some RF lines in this fridge and start measuring them. So we did that. Okay, so now here is some preliminary work that is related to the McDermott paper that I was just showing you. So here's charge spectroscopy in a normal situation where you, as Mike pointed out, there is already quasi-particle tunneling in these chips, and that means that you get 2 parity bands. So as I sweep charge bias on this thing, so here's frequency on the horizontal axis, charge bias on the vertical axis. So this is charge spectroscopy of a single qubit, but you get 2 parity bands because electrons move back and forth, and so the parity of the island is changing at a faster rate than the measurement. But so you get this sort of helical thing. And then down here, what's happening? You're mapping out these helixes, and then all of a sudden, boom, you get a discontinuity in the measured charge or in the energy levels. And that is because all of a sudden, we're not applying the amount of charge we thought we were. The amount of applied charge has changed in some discontinuous way, and that has given us a discontinuity on the spot. You can see also in a Ramsey measurement, right, where I've got applied charge on the horizontal axis and the occupied, the one-state probability on the vertical axis. You can see up here where there's no event, it's a nice sort of like a cosine curve. It's very easily fittable. And then over here, all of a sudden, boom, you get this discontinuity as well, right? So these discontinuities are the way that we measure the excess charge in our qubits. And so similar to the McDermott paper, now we've got a bunch of different configurations that we can show you. We've got shield closed with no source, right? So we're getting rid of as many muons and gammas as we can. Then we've got the shield open, no source. So we're sort of letting in some of the gammas, but the muons stay constant, or anyway, we think so. Then there's closing the shield, but putting a barium source on the inside with an activity that's kind of low, like half a microcurie. And then the shield closed with a cesium-137 source in there, where the activity is much higher by let's call it 2 orders of magnitude. And you can see that the more ionizing radiation is present in the system, the farther we get away from the origin. So you can think of it like a random walk, right? Every time some ionizing event happens, we push the amount of integrated charge passing through the junction farther and farther away from 0. And so the more steps you take in a random walk, the farther away you get from that origin. And so we're seeing correlations between the amount of ionizing radiation and the number and the number of correlated charge jumps. There's other aspects of this analysis that I'm not showing you because we're busy trying to write a paper about this. But anyway, here's the start, right?
Is it possibly baseline for 14 times?
It's about 500 kilohertz, if I remember right.
The previous slide, the data is showed is under what condition?
This is honestly, I don't remember. It's just an example event, but I think you'll see something similar no matter what shielding, right? The thing that the shielding and the sources do is they affect the rate of these
But you
things.
still observe these.
But we still, yeah, in every configuration, we get some of these, but we get more of them the more ionizing events we have. And sometimes we get even 2 of these jumps per Ramsey sweep. So in the case of the cesium. Okay, so what we're trying to do is, again, as I said, we're trying to decouple the effect of the muons from the effect of the gammas. But one of the other things we're trying to do is to motivate new device designs and new approaches to error correction that are not so sensitive to these processes. Again, we have transmon qubits whose T1 times don't really suffer from like low-level constant fluctuations in gate charge. What we don't have is systems that are robust to multiple qubits being perturbed by gate charge at the same time. And that's sort of something we want to think about.
The qubits were designed to be transmon. You didn't make them more like charged qubits.
They're weakly charge sensitive. So these have a Josephson to charging ratio of 24, I think. Right, whereas a transmon would be 80. Okay. All right. So we're learning what backgrounds are relevant for a qubit-based dark matter search. What other tools do we need? Right, it's not just about backgrounds. We have to characterize these devices. So we're running low on time, and there's a lot to talk about. So I'll go a little bit quick. There's another background that I want to talk about, and that is phonon bursts from stress release events in layered media. So if you have some sapphire and you put a superconductor on top of it because you're trying to make some layered device like a kinetic inductance detector or a transition edge sensor or a qubit, whatever it is, the interfacial strain at the interface between those two media takes a while to thermalize out. Yeah. Likewise, if you take a chip and you glue it down to some sample holder so that it thermalizes well, that's also some stress, and it takes a long time at cryogenic temperatures to pull that out. So here is a plot of 5 different semiconductor detectors where the horizontal axis is total energy deposition and the vertical axis is event rate. And so you can see that all of them are more or less flat, no dark matter here, until you get to these very low energy events. And all of a sudden, these bins down at the low end of the spectrum, they are all populated. And so that's 5 different detectors, all seeing the same low energy event. Hey, we found dark matter. Where's our Nobel Prize? Oh, it's probably not that. Probably it's glue peeling in a fridge, right? And every time you, the bimetallic effect, right? Where you got differential contraction between 2 media. And every time that contraction relaxes itself a little bit, you get phonons and you get some signal in your detector. And so trying to work this down, trying to sort out this background is something that Dylan is working on. I think he's in a meeting right now and is not in this room. But so he's talking to one of your colleagues here, Sunil Bava, and there's Elena in the back. Hi, Elena. Raise your hand. People can ask you questions later. Anyway, so what would be nice is to take some of these magneto-optical transducers and put them on our chips to be able to disentangle electrically interesting events from just strain release events. So having some coincidence allows us to discriminate between the events that might be dark matter and the ones that are just that source of background. So we're trying to develop this technology for dark matter purposes. Another thing that we're trying to do, so now what I'm doing right now, in case it's not obvious, is I'm going to go through a bunch of people in our group and talk about their work and how it relates to this and what tools we are developing to attack this problem from a dark matter perspective. So here is Ricardo Gualtieri, who is building a model of the fridge so that he can simulate particle interactions in different chips. This is a Monte Carlo model, and when I showed you this picture of an interaction in the CMS detector, I was showing you basically the same software doing the same kind of work, but just in a different energy regime. It's still particles interacting with matter, in a way which is classically determined. And so here we're just doing it for particles, I think from if I remember, an americium source impinging on the dilution refrigerator. It doesn't look like a fridge here because it's just geometry primitives, but you can see the wireframe model of the fridge here. And then here we've got the model of our qubit chip, which goes right into that model. So we can simulate the event rates and the energy deposition from our various known radiation sources on the chip. Then we've got Ryan. Ryan, can you raise your hand? So Ryan is working on this modeling problem, not only for that, just the sort of classical and ballistic problem, but then what happens when you strike the chip with one of these particles? What happens in the phonon spectrum, right? So here's the workflow, right? You got some scattering process in your chip. You've got energy propagation through the chip, and that's something that Monte Carlo program can model. Then you've got quasi-particle production, and then you get into stuff that needs this other software package called G4CMP, where we're simulating quasi-particle production and its dynamics in the chip. And so here we've got some quantum device response. It's tying all these things together in software so that we can simulate what happens in the qubit. So this is errors per 20 measurements versus time. And so you can see Ryan's work on sort of reproducing that Google measurement, right, of errors that occur in a chip due to quasi-particle burst events. But this is all in simulation, right? So now we've got the tools that we need to design number one, to study these processes, and then number two, to design devices that can respond to them. And so Ryan says he needs to be able to measure order 100 EV deposited in the chip to see more than 10% of the scatters with 2 or more qubits. I don't have time to get into more details, but we'll let Ryan do this. And so does this work? The answer is yes. So here are some experimental images of phonon caustics in different crystals in sapphire and in gallium arsenide. And you can see that G4CMP reproduces these very nicely. And so we do think we know what we're talking about when we talk about phonons propagating in these chips. What else are we doing? We're developing in-house fab capability. So is Sarah in the room? Sarah Sussman is with us. They're all having another discussion out there because they already know this stuff. They don't need to watch me talk about it. But anyway, so Sarah has been working at the Pritzker nanofabrication facility at the University of Chicago to build qubits for us. And so this is a 2-inch wafer with 25 chips. Each chip has 6 qubits on it. And she is demonstrating the ability to make different kinds of Josephson junctions. So there's squid arrays and Manhattan junctions here. And then she can make qubits with them, right? So here's 3 qubits on a chip. And you can see that at each one of these capacitive junctions, you've got a Josephson junction here. And so as we come up with ideas to test, if we want to try new geometries, if we want to try new materials, we've got people like Sarah working to help us with the design and fabrication part of the workflow. Okay, so then what about characterization? How do we understand the energy thresholds and the time sensitivity, the timing resolution of these detectors? Well, with lasers, basically. So we've got a group of people who have built a steerable laser source. So you've got here a movable mirror that takes a laser light, bounces it off the movable mirror, and then directs it onto a device under test. And we've implemented that in a dilution refrigerator. So this is a cryogenic micro electromechanical steerable mirror. So we've got laser light, which comes down a fiber into our fridge. Then at the cold plate, at the mixing chamber plate, we've got this copper box, which is very well thermalized. We've got the mirror that steers the beam. So we get this nice large area over which we can raster a laser beam, and we can direct that onto devices like qubits or other devices, right? So here's an example of this, just warm characterization. So the mirror is responsive enough that we can, draw the Fermilab logo, and, it's the standard academic trick, right, of bragging about yourself. But here it is being installed in the fridge. And the idea here, again, is to deposit known amounts of energy onto the qubit chip so we can measure the energy response at particular positions and the timing threshold. So if I deposit a known amount of energy at this point in the qubit, how long does it take the system to recover? What's the response rate of the information on the qubit? Okay, Furthermore, we don't just have the one test stand underground, we are building a full-blown facility. So we have a purpose-built clean room underground that we call Quiet. I'm not sure how the acronym is pronounced. I think it's lost to the lore. But anyway, so this was funded by the Quantum Science Center. It's got an identical twin to this up above ground, so we can do A/B testing, right? We can bring packages between an above ground unshielded environment and an underground shielded environment where we control the radiation very well, so that we can make comparisons. And so you can see all of us with, well, some very small fraction of us with big smiles after the commissioning of that facility. All right, so we're at the end of the talk. We're at the end of the hour. We're going to put it all together, and there's going to be time for questions. Okay, so what do we need to use qubits for particle physics? Well, we need resolution and sensitivity characterization. That's the steerable MEMS mirror that I was just telling you about. We need an understanding of our backgrounds. That's the work I was talking to you about decoherence from ionizing radiation and also from interfacial strain release events. We need device simulations. That's the work that Ryan's doing along with some students. We have dedicated low background facilities. So one of the nice things about this that I should mention explicitly is that, as far as I know, it is the only underground test stand that is dedicated to quantum information in the whole country, right? So there's other underground test stands where people want to do this work, but they share that space with other experiments as well. It's totally reasonable. But we have more throughput, presumably, in this facility than other people do. So there's more work that we are capable of doing. We've got the design and fab capability, so that when we have new designs to try that are less sensitive to these techniques or that can measure them in a different way, we can just build them ourselves. But then there's other things we want to look at, right? So moving beyond superconducting qubits, what if we need smaller energy thresholds than they can give us? What if there are novel materials that give us new sensitivity in different energy ranges than we currently have? What if we need to stop using qubits as pixels that are not coupled and start entangling them to get better sensitivity to particular models that we're trying to evaluate? And what else, right? So one of the themes of this talk is we know what we need for dark matter, but we don't know what tools are out there. And so it's entirely possible that other people outside of our field have the tools we need. And so I'm very happy to talk to you about this, and I hope that it has given you some ideas. So I'm done, and we can take questions now.